Okay. Hey, good morning, everyone. Thank you for joining us on the Monday Reinforced Concrete Lectures. Really happy to be with all of us again. Before we get started, several quick announcements. I finished the grading on exam one and the grade has been posted. If you haven't gotten the time to check on it, please do. Now, overview of the grades. We have average of this exam about 81 overall. So it's pretty good record. This is higher than the last semester actually for the first exam. So I'm pretty happy about it. And there are like seven 100 scores. That's very surprising and just very good news. And I have more than a dozen
Oh, I did not
students
get a series.
that have scored over than 90, which is very promising as well. On the downsides, we have about the same number, 6 to 7 students that have a failing grades below than 60, and a few students that are on the borderline, which is the passing grade, but have some problems. I have emailed the students that who has some troubles in this exam out already, and please stay behind if you're here today, and we're going to talk about some possible solutions to help you either improve your exam one grade and or your study strategies for this course. Since this exam is very critical, and by my experience, it tells a lot how students usually do in this course. So I strongly suggest you stay behind if your grades is uh, not really good, and I send the email to you particularly. All right. Okay. So that being said, I just want to quickly identify some of the key problem I've seen from the exam. Let me see if I can open up my uh, screen here. So where is it? Excuse me. So, all right. Okay. Can you guys see my screen? Anybody? Is it open up to you guys? Can you see it?
Yes.
Yes.
All right. Thank you so much. So several things, right? The multiple choices one, you guys are pretty good. And just on the strain diagram problem that few of us got confused. If you look at some of the problem, and this is different for everybody, right? For those students who have seen the strain diagram in problem set number one, and if you carefully observe the problem, which you should, there are some numbers written down here. Okay, particularly last row of numbers should be 0.0046 or something like that. And that actually corresponds to the last row of rebar. All right, last row of the rebar. So that is to say that when you calculate your phi, you need a strain for the last row of the rebar. You just need to pick it in this value here. You don't have to actually calculate it. Okay, so that is one of the issue here. Okay, you need to calculate the phi based on that. So if your phi wrong, naturally there's an under reinforced transition zone selection that you picked is erroneous as well. Okay, so that's a common seen problem number one. And the rest of the concept problems are I seen all of us I can feel we have a good grasp of them. So I don't see any significant problem. It's on the doubly reinforced section. All right, I have observed some mistakes. One of the mistakes is that when you look at the doubly reinforced section, right, you ought to notice that regardless of the bar position, regardless of the part position, okay, you always have to do the balance. That is, you want to use tension to balance compression or vice versa. But the problem is that you have to make sure that these are within 5% error best. Worst case scenario, if you leave at 10%, that's okay. But I've seen a few of you, some of you, that march down and tell me that, look, Bob, there's an error bigger than 10%. I'm just going to move on because I ran out of time. That's fine. I still give you partial credit for it, but ideally you wouldn't, reach that scenario where you have the trouble. And Trinity, the grade test posted anywhere, I believe is posted on Canvas. All right, so check again to see if you see it. If not, let me know. Okay. Now coming back to this problem, so you need to make sure that the compression and tension are balanced. All right. So the other question is that some of you may say, look, Bob, I know they're not balanced, but I don't know which direction should I move towards. Should I increase the compression zone or should I decrease the compression zone? It's very simple rule, right? So you think of it, the tension equal to the area reinforcement AS multiplied yield strength of steel Fy. So when your AS is fixed in the problem number 2, which is the case, your tension force is kind of fixed normally, right? So all you have to do is to see your compression, right? So when your compression is too low, what you naturally do is when compression is low, just when the compression is low, what you naturally want to do is increase the compressive zone, C. All right, but when you increase C, you have to watch out because the strain in steel epsilon S will drop and you will end up losing some of the strength reduction factor values, phi. Okay, and then when compression is high, and then you just need to reduce your compressive zone C, right? So once C reduces, your strain in the steel increases, and then your phi should be on the upper side, which is good, right? Which is good. So that is the common mistake. And then a lot of you guys, when you do the structure analysis, for example, if you see a cantilever beam, we have either the live load pick here or live load in the middle, whichever position it might be. But the critical information you need to find out the PL, the live load that satisfy the design, is to actually find out the stress reduction factor phi. All right. So some of you just left it there as a nominal design flexure strength and left there like this and went ahead and with this number to calculate your allowable live load. That is not right. That is not right. So be careful, okay? The essence of that problem is require you to compute phi. So that's a common mistake in problem number 2. All right, now problem number 3 is a design problem. So there are 2 types of problem I give in this exam, 3 version of it, and there are 2 similar problem like this. And of course, we change the number and position a little bit, but supposedly one is a negative bending moment and the other is a positive bending moment. Okay, so let's say this is section A and this is section B. So for the negative bending moment 1, when we ask you to draw the cross section, you really need to draw the bars on top, okay, because that's where the tension's at. And for section B, you really need to draw the bar on the bottom, okay? All right, so that's that. Now, for this problem, I see 2 issues. One is that still some students have trouble of estimating height, but very few, okay? So the height is estimated by the span length. You can check, okay, usually this number, and recall from the lecture notes. So it just need to have an initial estimation. And you can assume 1 row of bars, so immediately you can get h minus 2.5 inch as the first estimation of depth. And you go on and calculate phi-mn and make sure this is bigger than mu. If not, all you have to do is go back, change your age. Change your age. Okay, then redo the design. All right, so this is not so problematic. I see few students actually have more problem in another type of pole problem, right? Where you have a pole sticking out, and we tell you there's a bending moment equal to a pu multiplied by L. And we told you none of these parameters. We just tell you the final number, for example, 350 Kip's foot. Okay, I can't remember exactly this number, but this is roughly the number there. And then we ask you to design for it. Now, first of all, when the pushing force P go this way, it's kind of like a flipped cantilever like that, right? So the tension is on the top in this way. So this is the section. And when I draw the tension like this from the left-hand side, the bars is always going to be on the left. That's where the tension's at. All right, so first of all, that's the configuration. Second of all, I got some students, actually one student asking, so Bob, I don't know how to estimate the section height. And you talk about how we design it without a given section in the lecture. So I didn't study it because, this is before that lecture. You're absolutely right, but we have a limitation on the width. Okay, we have a limitation on the width. If we don't, you can assume a number, right? So all we have to do is just assume a span length. Assume a span length. All right. Now, what kind of number you want to assume? But by looking at this, by judging of this, right, I can say 12, I can say 10 feet, I can say 20 feet, I can even say 100 feet, right? It doesn't really matter. Why is that? Is because there are two criteria we talked about in lecture. One is that h has to be between 12, sorry, over 12 over 18. And the other, don't forget, usually h is bigger than b, than the width, right? So these are the parameters you can use, you can select. All right. Now you may run into the problem that initial gas of h and give you the depth of ds minus 2.5. That is not sufficient. You might end up with VMM smaller than mu. What to do at that scenario, right? You go back and change your h. And I guarantee you that you should get a design section that satisfies the requirement within 3 iterations. Within 3 iterations. Okay, now so this is the solution for the last problem. Now, second issue on this type of problem, actually for both of them, is check the detailing, right? Check the detailing. Now, I have seen a very good solution, right, on the moment diagram and on the moment design moment, everything. I was pretty happy. I was going to give you a full score, but then I started to realize when you draw the drawing, you become very careless. I see a lot of students are very Picasso like, right, artistic. It just draw like what I draw in the class when I run the time is just like this. So I look at this. If I were a construction manager, I look at this, I will feel very concerned because I don't have anything to go on. What is the spacing between bars? What is the concrete cover? And even what is the minimum beam width? Does it work at all? And at minimum, you have ACI table or textbook table A5, right? Table A5 with you. You can simply check whether your beam width satisfy that requirement or not. Even if you just did that, I give you the full score. At least you thought about it. But significant number of us just didn't even bother, right? They got a moment right, and they're happy with it, and they just left it and just put the bar in an illustrative fashion. So let the construction people figure it out, and that's not right. Okay, so we really have to check on the bar detailing for both type of problems. If you didn't check the bar detailing, I normally deduct 5 points out of 35. Okay, so that is that about the first exam. All right, like I said, overall, I'm pretty happy with the outcome. And just for information, if you step in late, there are 7 to 8, I can't remember exactly, students got 100 score, and the average is 80. And we have about a dozen that over 90, and still we have 6 to 7 that is falling below 60, and about 6 to 7 on the borderline. So if I send you an email, please stay behind, and let's talk about how we're going to address this issue moving forward. Okay? All right, so I'm going to stop right here, pause right here. Welcome any questions on the exam.
Professor,
Yes, sir.
I'm not seeing anywhere on Canvas the actual submission to see what I got wrong on it. I
Right,
just see my
right.
grade.
So you emailed the exam to me, so I graded on my laptop. And if you want to see the detail or discuss with me the detail, we can make appointment and we can talk about it. But
Oh,
right
okay.
now on the canvas, it's just a grade out there.
Okay.
I remember your case. Well, we can talk about in private, but I remember your case as well. All right. Okay. Anything else, folks? Anything? Like I said, if you have any particular question, I want to take a look at your exam, see where you did wrong. Welcome to schedule a session with me and we can go over them. All right. Feel free to do so. All right. So we're on the tight schedule. So without further ado, let me come back to the course itself. Okay. So first of all, I want to show you this picture here. Okay. This is about the T-beam. All right. Now, on the right top image, you see that we have a T-beam cross section, right? So we have on the left is more like an L shape, right? In the middle, that's the typical T shape that we have been talking about. So we have talked about the geometry, right? BF in terms of flange length. Okay. Now the labeling is slightly different because in the previous lectures, right, we use this as a BF, the total flange width as a BF. And now here I use this, right? So you can make some adjustment. The reason is that we have to introduce you the ACI table, which only determined by the one side of the overhand length of the flange. All right, so that's a little bit different from what we talked about previously, but it doesn't matter. Once you have BF, you add them up, you add the BW, which is the web width, you have the total flange width, and we call it BE, if you remember, be effective. Okay, all right, so let me just take this one on. Look at this image here. So in the section, you might have two locations, one on the left we call L shape, and one in the middle is called T shape. Now ACI table 6.3.2.1 has a very specific listing for how you calculate the flange width. All right, so how do we do that? It says that for the L shape, that is also called the spandrel, that we can use this equation. So BF is one side of the overhand that defined from the edge of the web extending into the flange that is a least of 6h. So what is h? H is the height of the flange. Okay, so I should say, if I want to be rigorous, HF. Okay, but that's fine. You can say H or HF as long as you know it's the height of the flange. Okay, so to label clearly, this is HF. So it's a least of 6 HF and SW divided by 12 or LN divided by 12. And what is SW? Now, SW is the transverse span length, that is distance from internal or inside of the web to the inside of the web. Inside of the web to the inside of the web. All right. Now, LN divided by 12, what is LN? So you look at this cross section here. Now, the span length along the cross section, which I draw here on the bottom, that along this direction, which is, if you look at it from a outer plane direction, that's an arrow shooting away from us, and that is the direction. So this is the LN. And so that is the third term. So one side of the flange extension for the L shape should be least of 6HF SW divided by 12 or LN divided by 12. So that is that equation. Now for the T-beam in the middle, how do we determine the flange overhand, right? Or the extension, right? So that is least of HF SW divided by 12, I believe. Let me make sure it's not a typo. Sorry, this is not 12, okay? I made the mistake here. I was feeling a little bit weird. So this is 2, okay? Just to clarify that. This is 2, okay? And then here is ln divided by 8. ln divided by 8. Okay, now this is all fine. This is all fine. But for the T shape, there might be some problem. Let me explain, okay? So first of all, let me get this exam stuff out of the way. Sorry about this. Just a little bit lazy, use this space here. So let's just get this out of the way. And you probably don't need this. If you have a specific question, you can always talk to me about it. Okay, let me just remove this for our sake of space. All right, so you may run into an issue. What issue, right? So say the T-beam here in the middle, what if I have, for example, this T-beam here, okay, and has adjacent T-beam, of course, right? It's continuous, right? This always happens. And now, for example, if I look at this T-beam right here, I want to determine the flange overhand, BF, say, and this is BF, say, right? So the problem is that when you say SW, you have two. We have SW1, we have SW2. One on the left and one on the right. How do we determine a BF in this case? Simple, right? So when you determine SW, you use the average. Okay, you use the average. All right, so that's how we determine the flange width, effective flange width. Okay, all right, so why do we mention this? Why do we need this? You see this in homework number 5, last problem, okay? If you don't have that problem, lucky for you, but in the exam, you see a similar issue like this, okay? Similar issue like this. All right, so that's all. So far, we have concluded the flexure design part for beams. Now, the only thing we'll touch upon in terms of flexure will be the slab, one-way slab design after shear and column. But as you can see that we spend quite a big portion of this course focused on the bending, which is flexure. So you have to understand how we operate on flexure. It's a very important issue. Okay, very important issue. All right, so now let me go back to see if I can open up this. Sorry, there's a little bit delay here. Okay, so let's talk about the next part of it, right? So graduated from flexure design, we're moving on to shear. So today, lecture 11, design for shear. Okay, now we're going to show you a whole different scenario, whole different conditions. Okay, so of course, the objectives are, okay, today's more conceptual, right? First of all is explain the variation of principal stress. Now that shouldn't be a new term, okay? That should not be a new term. You should have learned that from the mechanics materials class, all right? Principal stress in an uncracked elastic beam, okay? Now your brain should start flipping quickly, think about what we have learned before from mechanics materials class, okay? What is the definition, principal stress, so on and so forth, okay? Now the second, we need to be able to describe the shear transfer mechanism, okay? Of course, in RC beam, in reinforced concrete beams. Now that is with and without reinforcement, both. Okay, with and without reinforcement, both. Okay, all right, so now here is the concept, right? And if you want to read about it, you can find out them in textbook 6065 and 64. Okay, 6564. Now, first of all, let's talk about shear design, right? So 11.1, first thing, shear plus diagonal tension. Okay, diagonal tension. All these are new terms, so watch out for it, okay? Diagonal tension. All right, so before we start everything, let's review a little bit mechanics and materials, okay? I want to take a look at the stress. In an uncracked elastic beam. It means no crack, meaning in terms of concrete, if I draw the stress strain curve for this type of scenario, it stays linear, okay? This is the presumption, right? Now, if I have a beam, I'm gonna use a different color to make it more distinct. And let me make it big as well. So anyway, so this is the beam. It has a depth and rectangular section, of course, and I have a support underneath it. Well, this is actually a roller support. Okay, this is my habit. When I draw a cross, means it was constrained in both directions. When I draw only one line in vertical, it means only constrained vertical, not horizontal, right? So you probably figured that out already. But anyhow, so the distributed load is applied to the beam. We have a distributed load applied to the beam. And we want to take a look at the stress in the beam. Right? So naturally, since the beam is elastic and is uncracked, there's no crack in the beam, right? So we can conclude that it's going to be a neutral line. There's going to be a neutral line sitting in the middle of the beam, just like that, right? And then we can draw out the stress distribution for this from mechanics materials, right? So naturally, we're talking about the middle section right here, right? So let me call it section AA, right? So on section AA, what the stress looks like, right? So since the linear elastic, so the stress strain all follow a triangular distribution. So it goes like this, linear line, okay? And top is in compression, of course, and bottom is in tension because it's a possibility moment, right? And then the maximum stress equal in magnitude is both in compression tension, both end of it. So that is the what we call it normal stress, right? Remember, normal stress. What does normal stress mean? Meaning the stress is in perpendicular to the cross section, right? That is normal stress. All right. How about shear? How about shear? So if I draw the shear that from the equation of shear, right? What is the stress equation for shear? So this is still AA, and this is shear stress, right? Well, before let me finish the equation for bending. So for normal stress, right? The equation is what? So bending or normal stress, Y, it is linear, right? So because the equation reads like this, so F, which is the normal stress, and that equal to bending moment M multiplied by Y, which is the distance between the neutral axis to the extreme fiber, in this case, half H, right? But anyway, this is Y, right? Distance, right? If it's here, Y is here, right? And My divided by I, which is moment inertia, right? That's the equation for bending stress. You see that this is linear relationship, right? Linear relationship. My multiplied by Y is linear. So that's why the line is linear, right? For shear, okay, just say shear stress, right? What does it look like? Because shear reads like this, tau equal to V, that is the shear force. Total shear force acting on the section AA multiplied by Q is the static moment, right? Static moment divided by I, moment inertia, and multiplied by the width in the middle, and B. So observing this equation is more parabolic. It's more parabolic shape. And that's why the shear stress behave like this. Okay, behave like this. And it's 0 at both ends. And maximum value in the middle. Right? So that is the normal stress and shear stress on cross section AA. Cross section AA.
Professor,
Yeah.
what'd you say Q was again?
Q, where right here, is a static moment, right? So Q is defined as how Q is defined: area multiplied by distance and integral by area. Okay. Wait, let me see. Area distance is integral by distance area. Area distance dA. Oh, sorry. Let me just remove this. Yes. Okay. So this is what it is. Okay. So you think of it, right? So if I have a potato, and this is the neutral axis, okay, and I have a strips of dA here. Now dq equal to dA multiplied by this distance, which is r. Okay, hence if I want to do the q, I need to do integral, and this is what it is. Okay, and this is called the first moment or static moment. It's basically area multiplied by distance. Okay, and if you really want to know now, if I have r squared dA, and that's called the second moment, right? Second moment. But anyway, we don't need to know that for now. Okay, so this is first moment, static moment Q. Okay, and if you forget how to do that, you can recall mechanics materials. Okay, mechanics materials. But anyway, this is the shear stress and normal stress composition for the cross section AA. For the cross section AA. Okay. All right. So what we are really interested to find out is this: is what type of stress combination we see, and more specifically, what kind of principal stress we see on the element. All right, on the element. So I'm going to take a look at the stress distribution in normal direction. And let me switch color. Normal direction and shear direction. Now realize that if I look at the middle neutral axis, I have 0 in normal and maximum in shear. So if I draw an element right here, right on the middle axis, a small element, right on the neutral axis, small element, element 2, then I can conclude that element 2 is in pure shear because there's no tensile stresses or compressive stresses on it. Okay, right? And then if I move up here, just pick a random spot on the in the upper portion of the beam, and I realize that it basically sustains a compression force, compression stress and shear, right? And shear. So let's just do this. So it goes up. So this surface goes up, and this goes this, and this goes like that, and this goes like that, right? And for 2, it's pure shear, right? So it goes either way, but let me just shoot the direction this way. Tail against the tail, head against the head. That's how we do the linear momentum conservation. Anyway, bottom here, that's 3, right? And 3 should see tension. Is that tension and then shear, right? Then shear, and let's go to the same direction, right? All right. So now I have 3 types of elements. I'm going to see what exactly the stresses are in these elements. Okay. So first of all, let's take a look at element 1, right? So switch back, element 1. It's a little bit boring part of the lecture today, but it's very important. Okay. So I have element 1. Let me just take it out from the beam. Observe that I have normal stress going this way, F, and I also have shear stress that's going downwards, okay? This sign is a little bit different from here, so I'm just gonna correct this. Probably doesn't matter because it depends how your sign convention goes, okay? Depends on how your sign convention goes, but that's fine with me. Let me just follow through, make sure they're consistent. Okay, all right, so they'll go down, and this of course go this way, go this way, go this way. Head against the head, tail against the tail, okay? Head against the head, tail against the tail, okay? All right, so that is the shear stress distribution. So this is that, and this is that. All right, so what about the principal stress, right? First of all, the definition of principal stress. Now, recall from mechanics materials class, the definition of principal stress is that I can rotate the block or the element to a direction that I don't see shear anymore. I only see tension or compression, isn't it? So that is if I rotate the block from this upright position to an inclined direction with the angle of alpha. Okay, this rotation angle of alpha here. Okay, and we can actually calculate that, remember? But anyway, if I rotate in that direction, I realize that what I end up with is going to be pure tension and compression. Tension and compression. For instance, this is pure tension, for example, and this is compression. And even further, I can calculate this. The tension and or compression, 1 or 2, okay, is going to be half of the compressive stress applied to the normal block plus or minus square root of F squared divided by 4 plus tau squared. Okay, and I also know the angle from the mechanics materials class, tangent alpha, actually tangent 2 alpha here, 2 times alpha here, equal to 2 tau divided by F. Okay. All right. So why this is important? Because I want you to take a look, right? I want you to take a look. I will define this as the major tension direction. This red line here, okay? And just put this in your mind. So this is called the tension direction. Meaning along this line, I'm gonna see tension at this spot. Okay, so that is element 1. That is element 1. So let's take a look at element 2, right? Element 2, right? We have it just pure shear, isn't it? Pure shear is on the neutral axis. So it's on the neutral axis, and the element 2 looks like this. I have no tension, no compression. I just have shear stress. Again, head, butt, head, butt, right? And now that is the pure shear state. But nevertheless, I can still rotate it and to get my principal stress. Okay, and it turned out that for pure shear, I can rotate it to a 45 degree. For pure shear, I can rotate it to a 45 degree. And this is actually not 45. Forgive me on my horrible drawing. Let me just get it straight. So If it's 45 degree, it looks like a diamond, right? If it's 45 degree, it looks like a diamond. Okay, so I have a blue in terms of compression and tension. That is the principal stress. I have my angle center here, alpha here. Now this alpha angle here, we know is a 45 degree for pure shear. Okay, for pure shear. And now if I want to draw the tension line, like I did for element 1, I can still get it, right? Like this. And that is, again, the tension direction. Tension direction. Now, we have done element 2. So element 3 is a little bit different, right? Element 3 is a little bit different. Why is that? It's because it has compression now. It says compression now. So 2, we have, sorry, it has tension now. We have tension. And we have shear going this way and going this way, going this way, going this way. All right. Okay. So now for this, the tension goes like that. Same thing as this fellow here, okay? But it just have a different angle. I will try to get the angle right, but it's actually more flat. It's actually more flat. Okay. This alpha angle here is smaller. Horrible drawing, but anyway, this alpha is smaller. Okay, so the tension direction is this guy here. Okay, so this is tension direction. All right. Now at this point, I must have confused all of us already, right? And I keep saying tension direction, tension direction. What are we trying to do? This is what we're trying to do. So after all this exercise, I realized that all these elements have a major tension stress, principal tensile stress, that in this diagonal direction. Okay, all these tensile stress are in the diagonal direction. And this is so-called diagonal tension, isn't it? Okay, and if you're still confused about it, now remember these 1, 2, 3 are pick spot by random, right? They're only in relationship of height. They can be anywhere horizontal direction, right? So essentially I can move this one to here. And don't mind my blue line here, I'll make it up, right? And I can move my 2 into here. All right, and turns out that I can draw my diagonal shear stress, that's our diagonal tension stress, in terms of same magnitude. Okay, and follow the shape like this, and symmetric like this. Okay, and every spot along this line have the same magnitude, and the tensile direction is along this line. So I can keep drawing it. Kind of finish this trajectory of principal tensile stress. As you get lower, the bottom portion get flatter, and then the opening get wider. Okay. So these red lines are diagonal tension, right? Diagonal tension lines. Diagonal tension lines. Okay. So that you can think of it, they are the primary tensile direction. So the concrete being stretched along these lines, Okay. So when you're trying to break something, you stretch them, right? And then the failure or the fracture is going to happen in perpendicular to the tensile direction, isn't it? So that is to say the crack will occur in perpendicular to these lines. Okay, let me finish this, right? So in perpendicular to these lines. Yes, anything? Okay, so I will have cracks like this. cracks like this, right? So perpendicular to these lines, perpendicular to these lines. Okay. Okay. All right. So as you can see that as my cracks are getting away from the middle span, right? From section AA, it's more diagonal, right? Diagonal, right? And these are called shear cracks because as it gets away from the middle section, my bending moment is getting smaller. Remember the bending moment diagram from a distributed loading? It looks like this, right? So as you're getting away from section AA, right? Moment diagram. And my moment is getting smaller, right? My moment is getting smaller. And my shear is getting bigger. My shear is getting bigger, right? And the shear diagram looks like triangle, actually, sorry. Looks like this. Shear. Right? And as I'm getting closer to the middle section, I see my cracks is more vertical. So these are the flexure cracks. And apologize for this very crowded drawing, but I just want you to see the whole picture. Okay. These are the flexure cracks. Okay. And that's the reason why we went through so many trouble to show you the principal stress in the beam, because these are the failure modes that the elastic beam look like. Okay, failure modes of elastic beam look like. All right. Okay. All right. So now you know the the crack direction of a concrete beam. I'm going to pause here. Any questions on this? Any question on this concept? Anything? Are we okay? All right. All right. Let me quickly march on a little bit. Okay. So now we know. The beam is going to fail like this if I don't provide any reinforcement. Okay. If I know this, I'm going to take the failure diagram. So I call this failure diagram now because I know where the crack's going to be, right? Right. So I'm just going to crop it out. I say, look, I know this is theoretically how it's going to fail. I know theoretically this is how it's going to fail. And let me clean up the things are not necessary, right? The element block, all that crap, the trajectory lines. I don't need them anymore. I got my final wishes, right? This is what I'm looking for, the crack mode, right? And I even don't care about the names, diagonal tension anymore, although you should really care about it because we'll ask you about it in the exam. And support is right here still. I want the supports to show. Okay. And then I just have the cracks. Okay. I just want to have the cracks. So clean up this, and I only have the cracks like this. Let me make up this one symmetric. All right. And let's say as it get a little bit more in the middle, it's get more flatter. So just to exaggerate, let me just draw this way, get more flatter. Okay. And I'm going to design my reinforcement accordingly. Okay, so how do I design it? So if I use purple color to represent my reinforcement, I observe that there's going to be cracks, vertical cracks at the end of the beam anyway. So I'm going to provide a dowel or the tensile reinforcement we already provided, right? And these will help to resist the cracks this way. And that's how we spend almost 1/3 of the course study how we design this reinforcement, flexure reinforcement, right? So this is the flexure reinforcement. But since they're connecting the crack pieces, we can also call them dowel effect. Okay, so in short, these are also called longitudinal reinforcement along the span direction. Okay, longitudinal reinforcement. All right. Now that is fine to take care of the cracks in the bottom, right? The concrete cracks in the bottom. How about the cracks in a diagonal direction? In a diagonal direction. So for these, I'm going to have a different reinforcing strategy. I'm going to put transverse bars. From side view, it looks like vertical, but transverse bars to resist these cracks. And I will provide a hanger bar to loop them through it. Okay, to loop them through it. So these are the stirrups. Okay. These are the stirrups, right? Or we also call them transverse reinforcement. Okay. All right, so that is why we reinforce our beam in the fashion looks like this at the cross section, right? So I will have my transverse bars at the bottom, sorry, longitudinal bars at the bottom, okay? And I have my hanger bar, meaning they just be there as a compressive reinforcement to hand stirrups, hanger bar to hand my stirrups like so. And these are my transverse reinforcement to resist the diagonal crack. So this is for shear, essentially. This is for flexure. Okay, so all we have done is has focused on the flexure, and now we're going to talk about shear. All right. Okay, so this is a good point to stop. We're going to talk about lecture 12 on the shear mechanism and how we design for it. Okay. Now, if you have any questions, please ask right now. If you don't, or if you haven't gotten any, please see me tomorrow, 2 o'clock office hour, we can discuss. Apart from that, students I emailed to stay behind Monday class, please stay behind. Okay. All right. Thank you very much, and see you tomorrow, or actually see you on Wednesday. Okay. But don't forget office hour tomorrow, 2 o'clock. Thanks.